All right. Thank you guys for coming to our talk. I know it's after lunch and no one wants to be here, but but no. So we're going to be talking about hopefully something that interests everyone. This is model upgrade schemes and considerations for updating production models. Before we get into the presentation, let me introduce myself and Emmanuel. I'm a machine learning engineer at NYC. I was a REX research scientist at NYU with lots of my research focusing on AutoML as well as data provenance, and then by trade, I'm an electrical engineer. Emmanuel Naziga, also machine learning engineer. He's going to be taking the second half of his talk. He has a PhD in computational science, as well as his postdoc research was in computational biophysics and genomics. Finally, a bit about the company, because not many people know what Munich does. Munich Re is a reinsurance company, so that essentially means insurance for insurance companies. And how that essentially translates into the business is where we are a B2B company, so we work with lots of insurance carriers throughout the US, and we try to semi-automate their underwriting or data processing needs. This also means that because we're working with lots of financial data, lots of health data, we work under this interesting intersection of regulations, whether it be data regulations pertaining to, let's say, GDPR or CCPA, if it's California, or every state has its own really high level of regulations for insurance providers, so we have to look at all those regulations as well. And then, of course, anything that has to do with health data or like involves PII, which is personally identifiable information, we have to also regulate by HIPAA. So that's a bit about the company, about us, but that's not what the talk is about. We are going to be talking about how to update your models in production, and this is how we structured it. I'm gonna pose a problem at the start where we had like a model, a production use case, a prototype essentially that made its way to production, and sort of how we sort of developed it into a full-scale production pipeline with continuous training in there, with monitoring in there, and how we use the 4 C's of MLOps to get there. Then there will be some, I'm going to walk you through our exact process with the continuous training pipeline and some of the considerations that we had along the way. There's like lots of general advice in there, of course. And again, these are very, very use case specific. Every use case somewhat varies, but these were really helpful for us essentially to follow. It's like a recipe, essentially. And then finally, we're going to be talking about model validation, and that's when I'm going to tag him in, and he's going to be talking about the statistical comparisons we did when you're comparing two classifiers. So think of it as like a model called a CM, where 2 models come in and 1 leaves, whichever is better. And then he's going to talk about all the frequentist tests we did and the Bayesian strategies we applied, and how you can decide that on the fly. And then finally, he's going to end it with other considerations for us as an industry, in the industry, as an insurance provider, but apart from that, other considerations that might be useful for people generally thinking about continuous training pipelines. Yeah, so let's go over where it all started. So this is one of our products. One of our carriers wanted us to semi-automate their needs. They're like, hey, we have all this policy information. Can you somehow automate the underwriting, which is like risk classification of these policies? And you're like, the first stage of that would be, are these even eligible to be automated? And that's like, do you do a bunch of business? You have like a list of different requirements. Like, let's say if a person has a specific disease, cancer or something, you can't really automate that. You have to have a person look at that policy in more detail, so you can't really automate those. And so they're like, but if you can automate those, if they follow a specific criteria, then how do you assess risk class for it? And this essentially is what our data scientists built, where there was a data warehouse with all these policies, and parsing pipelines, which would take in the data warehouse data, then some pre-processing work, converting it into more schemas, some EDAs and kickouts. So kickouts are business use case filters, and EDA is exploratory data analysis. Then feature generation, model training, evaluation. A pretty traditional data science problem. Every data scientist knows how to train a model, and this is what the pipeline looks like. But once you have this data science strategy set up, you don't really know how to serve it in production. And that's where that's because this was a prototype, the easiest solution back then was take the model, take it into a pickle, convert it into a pickle file, and sort of push it into a registry. And then from that registry, ingest it into a prediction service, followed by an app which will be interfacing with your client. And this is what we also call an MLOps maturity level 0 deployment, because it's very well defined in experimentation. But when you're talking about production, it's kind of wonky. You don't really want to have something like this when you're serving a big client. And so, it doesn't mean that this is a bad solution. ML level 0 deployment maturity deployments are very good when you're prototyping and for speed to market. But we wanted to scale it up, and the way we did that was we used the 4 C's of MLOps: continuous integration, delivery, monitoring, and training. We borrowed the CI/CD from our brothers in software engineering, from DevOps, and what they stand for is continuously testing your code when it's in production, when it's being rolled out, just so you have the best quality of your code bases, which is very highly reliable, essentially. And then continuous delivery would be taking all of this stuff and package it, and then pushing it to a place without a middle person involved. A human shouldn't really be involved in this loop. So packaging your code, packaging your reliable code, and these CI/CD in software engineering really help you develop pipelines which are reliable. They help shorten delivery cycles. They have like their own benefits. But we talk about when we talk about ML systems, we have to also incorporate continuous monitoring and training into the equation. And continuous monitoring would help you drill down into the performance of your model. You should have good insight into what's happening with the data, with the model, everything that surrounds the model, the whole pipeline. And that's what continuous monitoring is about. And once you have identified a problem, then you should have a training strategy, for example, if you need a training strategy, and use the training pipeline to sort of update your models. So this is what we sort of started with. We wanted to have a CI, CD, CM, CP situation set up in our ML level 0 deployment. And so this is how we essentially did it. So actually, just before I get into the process, there's like this one part of the pipeline that I did not mention so far. So this is what it looked like in production. There was a user talking to the app, which was interfacing with the prediction service. And the prediction service was talking to a production database, which would be storing everything that comes into your prediction service. Let's say a policy comes in. It would be stored into the production database along with whatever the prediction was. And we track all of these. And there's like a hidden feedback loop in the background, because we want to monitor the performance of these models, and a feedback loop essentially requires us to take some data out and manually label it, as our industry has. Like, we can't really automate this process. It has to go through a person. So what we do is we take a segment of the production data, randomly, a random holdout set, which would be labeled by subject matter experts. These experts would then label this data, return it to us, and we'd use this as a proxy for model performance. So say, and essentially use this model performance to monitor how fresh the model is, how it's getting stale or not. And then what's really cool about this part is that you can actually use the data that they return to retrain our models, essentially, and make our models fresher over time. But that's what the feedback loop looks like. But essentially, when we started this, the first part was identifying if problems come up. And we had to sort of incorporate a monitoring service. So let me introduce to you in this diagram Emily, the MLE. And that's my only joke in this presentation. But Emily, the MLE, can now talk to a monitoring service. The monitoring service has good insight on what's happening on the production database. What's really important for Emily to do at this point is talk to all the different stakeholders, talk to business counterparts, talk to software engineers, DevOps, everyone who wants to monitor stuff, to sort of have this as part of the monitoring service. So there's like one box in to see everything that's happening in the pipelines and in the production data. A good monitoring service, of course, has business KPIs in there. For us, it would have been like the number of automated cases per week. It could have been if there are some specific reason codes. So when we sort of produce policies, we have to, when we sort of we produce risk classes, we also have to give a reason, essentially, of why that risk was classified as this risk and not a better one or a worse one. And that's just like one of the regulations on us. So, so let's say if there's a more prevalent reason code than the other, we have to also specify that. And so that could have been one of the key business KPIs. For performance, it could have been, it was something more towards software engineers and DevOps requirements. So let's say traces and all the other, is my model performing in the expected time frame that it's supposed to return a response, and what do the traces look like, and other business software engineering metrics. The data metrics would be more geared towards what the data looks like. So you would want to see what the distribution of the predictions are like, or let's say, what does the correlation between different features look like. So having all those metrics in mind, you come up with like a list of code bench metrics. And the next step is identifying acceptable thresholds. Because to be able to pinpoint problems, you need to have acceptable thresholds. And once you have those thresholds, you can sort of be a little more confident about what's happening in the model and the data. The next stage, once we have a monitoring service set up and we know what's happening inside the data, is to sort of talk about triggers. And triggers are essentially, so triggers are essentially your way to, once you have the problems identified, you want to be able to trigger a retrain if it's necessary. And the retrain should be, it could depend on your performance, on the model performance, of course. All right, give me one second. Because I got lost because this timer says I'm in 25 minutes, but I don't think I'm in 25 minutes. Yes. All right, cool. So yeah, so going back to the monitoring service, once you have the monitoring service set up, you need to have good triggers, and a complete solution would be able to retrigger a continuous training run under any of the following circumstances. It would be able to run on whether new data comes in or performance degradation is monitored by the monitoring service periodically, which was one of our use cases, because our labeled data would come in intervals, and we could train our models essentially quarterly. And then upon stakeholders' requests, of course, because data scientists love to have fresh models. But one should also remember at this point that there can be false alarms. You shouldn't always rely on, you should rely on the monitoring service, of course, but you should have a deeper understanding on what's happening in the model as well. Because there could be something wrong with the data set, there could be something wrong with the code that actually is getting you to that, getting you the data to that point. It could be something wrong with the pre-processing. You should be very, very comfortable, and this goes back to having like good fleshed out CI/CD pipelines where you should be able to identify these bugs before they happen. So yeah, once you have the triggers set up, you are confident in what's going to trigger these runs. It's devising a data selection strategy. Now, remember the goal of this entire CT pipeline is to have highly relevant models performing optimally. But one should remember that recency does not necessarily equate to relevancy. It's possible that the newest data essentially isn't representative of what the model is expected to do or expected to do. So one should have that in mind before deciding which approach to use. There's a naive approach where you could just use the newest data set and train your model against it. Or you could use like moving windows where you start looking at, let's say, the past 5 weeks of data and backtest it essentially against your model. Or you could also have dynamic windows where let's say, the window size is a hyperparameter of your model training run. So you could retrain a model and like window size, and you optimize essentially on the window size as well. But and that's one of the strategies I think we used. I think for us was using new data and old data originally to combine them. That worked very well. Also because like our model lifespans are so huge, drift comes in gradually, and so we can get away with lots of things that, like, let's say, a recommendation system for shopping recommendations might be able to. So I guess the next step is I should also mention that a delayed feedback loop again means that can mean that the labels are no longer valid. Ours was 3 months to 3 months. If you're getting labeled data in 3 months, that's fine. But again, going back to a shopping recommendation system, if your feedback loop takes like 3 months, that's probably not the best feedback loop. And then finally, enforcing extensive data validation checks is very, very important at this stage as well. remember that we do not want to ingest bad data into, especially an automated pipeline. That's not good. I would recommend using feature stores because you could monitor what the quality of your data in feature stores. You could have transforms in there, and every time data is ingested, you can have validations and like what you're expecting essentially. Using feature stores is very, very helpful sometimes. Okay, so we have data. What do we do next? I think the next stage is deciding the extent of the retrain that's required. Now, when we started, we wanted to train a model on the latest data or like a subset of the latest data, depending on whatever our data selection strategy was. But let's say there's a use case where the business needs changed essentially, and that necessarily translates into a model upgrade situation. Continuous training pipelines are great if you have a feedback loop which doesn't really require you to, let's say, change the model in any way. You just use the latest data and refit the exact same model with that data information. But if you've had to change your model, let's say the business needs changed, or let's say your feature engineering change or something like that, then you should probably take this back into experimentation and start with the experimentation part and have the experimentation decide what the best model is, then push it to production, and then have that as part of your continuous training pipeline. So updates and upgrades are kind of different there. The update, if you're updating your model, that's ideal. Continuous training pipelines should ideally be identical to their experimentation counterparts. Also, one very important thing is to maintain, retrain, run metadata. Remember that anything fails, we need to have a full fallback option, and we should be able to go back to whatever our previous run essentially was. Okay, we have a new model now, and with the new model, what we want to do is test if this is a better model. The first thing to ask is, what even does better mean? Right? It's essentially, it's what the business decides. If you're talking about, let's say, other considerations, if there's fairness considerations, bias considerations in your data, then you have to talk about what a better model essentially is. And then also, like, does it solve like the use case in a better way, or like is this updated model actually producing better predictions, or is it producing, let's say, it's the same amount of predictions before the degradation sort of happened? I think one way to test model validation, how people validate their models is, there's two ways essentially. There's an online version and an offline version. In the industry, people talk about canary deployments or blue-green deployments, or if you want to go really fancy, you can talk about multi-armed planted deployments, where you're actually having these models test in production. There's offline strategies which apply more to us, where you have, let's say, you can do predictive quality assessment, where you assess the quality of the model, right? Similarly to how you did in your experimentation phase, just how you evaluated, you did the evaluation there. Then you can also talk about comparing performance across different classes or against different baseline models, or you could essentially have more statistical techniques that push, that decide whether this model is better or not. And so for us, for example, we wanted to go much deeper into what a better model is versus another. And that's what we actually wanted to spend more time on, because each of these different parts could be its own talk, but model validation was something that's really dear to us. And so we have, I'm going to switch the conversation up a bit, and I'm going to have Emmanuel take over, who's going to be talking about our validation strategy, about the frequentist and the Bayesian tests that we did, and then how we come up with a better model essentially towards the end. And then he's going to finish with the other considerations that we have in mind. So I'm going to give it to Emmanuel, and thank you. I'll see you in a minute.
Hi. Thanks, Manaf. I am going to talk about statistically compared models, in such an automated retraining or pipeline. So basically, you have a model, a previous model, and then you train the new one, and you want to kind of evaluate and say, which of these are better, like on average, and what should I go ahead with? And so I want to do this in a statistical manner, and not just test on one data set or make one point, estimate point calculation and say, this accuracy is like 10% or 5% better than this, so we're going to go with this. And so that's what motivated this part of the discussion. And I'm just going to go over some techniques that I use for this kind of analysis and show results of some experiments that I run to kind of test this on a test set of data, and to facilitate discussion, and then conclude with looking at other considerations, other things we look at beyond this kind of validation for why use case in the health insurance industry. So a very common thing that people use in situations like this is, of course, the very, very popular t-test. So you have a bunch of average, differences in accuracies between two models. You can make a difference of them, and then you can set up a t-test, which you can set up your hypothesis that the main difference between them is kind of greater than 0, or it's not the same as 0, and then you can go ahead and kind of like do your analysis and come to a conclusion, accept or reject the hypothesis, pick a model based on that, and go ahead. Normally, this is kind of like implemented in the context of like CV, so cross-validation, where you kind of like have different folds of data and kind of do this analysis on the different folds, on the results, that metrics that come from the different folds of data. What happens is that because there's a bunch of overlap with this data, when you calculate the variance that goes into the denominator of this, the statistics that are shown on right, you have like correlation effects that kind of like introduce spurious type 1 errors that you don't want to kind of like see happen. And so because of this, there have been adaptations of this model to kind of like handle some of this, and that's some of the methods I'm going to talk about here today. One of them is the correlated t-test, which was put together by this work by Naziga and Benjio. So basically, I have this here just to kind of point out what's the difference between this and the previous method that I looked at. But basically, you introduce this heuristic, kind of like an approximation for a correlation, which is dependent on the number of samples you have in your test set and your training set. And then you use that to kind of like modify that denominator to kind of like handle that kind of correlation problem. And then you have the same, at the end of the day, you have a similar statistic that follows the same distribution, and then you can follow the entire machinery of the work and accept or reject the hypothesis based on the outcome of that analysis. Another method that I saw in the literature when I was looking at this, and I have, I forgot to mention earlier, but I have references in the bottom, so if you want to look this up later and look at the details and how these things were done, you can do that, and I think this video is available to look at that later on. But basically, there's this other test that was put together by Thomas Dietrich, which is called the 5-2CV paired test, which has this interesting algorithm where it takes around 5-fold of a situation where it takes the data set, splits it into two, trains algorithm A, for instance, on one of them, and then tests on the other, and then trains on the other, and tests on the other fold, and does that for algorithm B. So you have this kind of like 4 quantities that is used to calculate a kind of modified variance in the top of the right-hand side, and then that goes into the t-statistics that is in the bottom. And in the analysis, they were able to like show that the statistic that's shown there is now follows a student distribution with 5 degrees of freedom, and then once that is established and you do this, you can again go ahead and do everything, make a decision about your things based on statistical tests. So all this method and a few others that I looked at were all kind of like frequentist type of analysis with rejecting the null hypothesis based on like a p-value and choice of significance. There's a problem with that because sometimes that can be a little arbitrary, and like people have a lot of concern about that more recently. So I decided, in addition, you have this original problem with when you apply this in the context of a CV results, you have correlations, kind of spurious correlations that you want to handle in a kind of an ad hoc manner. So because of that, there have been some work recently in the application of Bayesian methods to kind of like compare models in this kind of setting. And so I introduced the Bayesian correlated t-test that was, and I'm following the treatment in the reference below. And like the key thing about the way they went about this is that they model the kind of this vector of differences by, of course, the mean you're trying to kind of like model, and at some of that mean, and a kind of multivariate normal noise with mean 0, and a covariance matrix that's the off diagonal elements represent the variance, and then the off diagonals kind of like tie into the correlation we were talking about. So if you applying this method in the the CV setting we talked about earlier, it's kind of natural because it covers the things that you want, that you're concerned about. Being a Bayesian kind of like analysis test, what you end up with is a probability distribution of the posterior, which is something you can query to make, and the outcomes of that is very straightforward. They're probabilities, and you can say this is the probability that this model behaves in a certain way, which is very different from the setting of a hypothesis test where you just accept or reject a hypothesis based on some arbitrary p-value and confidence interval. Something else that I'm going to talk about a bit more in the next slide as well is this. In this kind of treatment, they introduce this kind of like concept of something called the region of practical significance, which is kind of a nice way to kind of decide how models are close enough for you to say that they are practically the same. And I'm going to talk about that a little later with some visual aids to kind of make things a bit clearer. And so, as I have kind of mentioned previously as well, you end up with a posterior distribution. In this case, in the treatment they did, it actually turns out to be a student distribution, which is something we know. I mean, we are conversant with in Bayesian analysis or like in statistics. And this distribution describes the distribution of the difference in accuracies, for example, in this case, the particular case we're looking at right now. And so, if you look at the figure on the right, in that density plot, you see these two orange lines, and that's kind of like the region around 1% around zero. Sorry, 1% around zero in the difference in accuracies, which is kind of like a number you can decide beforehand and say resolve that within 1%. I consider those to be equivalent, and so you can define that and then obtain the probability that your model is actually the same based on that, and that's just given by the density that is enclosed in that between those horizontal lines over there. And then to the right and to the left, if you do kind of an integral over that or a summation over that, it gives you the probability that maybe a model A in this case, in one case, has such a probability of being the better model, and vice versa, model B has this certain probability of being the better model. So it's a bit more straightforward interpretation of kind of like this analysis, going forward. And so I am just going to give a brief kind of overview of the experiment that I run. The models we are looking at, as Monaf already intimated earlier, are like risk classification models that we use in the business in life insurance and underwriting in general. I'm using an accuracy metric here, but of course the metric could be different. This is just kind of historic based on the legacy of the particular application with around 70,000 instances of data, and looked at both kind of upgrading or updating schemes. A lot is going on in this table, but I'm going to work through it, and hopefully it's going to make a bit more sense as we progress. But I just want to say before going forward, the first three rows kind of show is kind of like an upgrading scheme where I'm comparing the results of applying of a random forest kind of classifier to a logistic regression classifier, and the bottom three rows are a random forest and a light edge GBM classifier. And I'm just going to go over each of the columns to kind of explain what they mean. So model A, of course, means that this is the model that was used in this particular test. Same with model B. The next column is what the analysis decides is the best model out of this. What particular test or analysis that I actually implemented in this case. The next column, so the average score A, is what the average accuracy for model A was in the test, and the same thing for model B. The next one is what is the region, what was used, and what percentage within the accuracy was used as the so-called region of practical equivalence in this experiment. This, of course, only applies to the Bayesian test because that is the only situation where it applies. Probs A is kind of like short for probability, but basically that is the probability that model A is the better model. Props rho means the probability that both models are kind of equivalent. B is probability that B is the better model, and p-value is just the p-value from the frequentist analysis. So as I mentioned, let me go back one step. As you can see, like in the logistic regression case, logistic regression of a random forest is very clear if you look at the accuracies that there's some separation between both two class of models, and so all the test types are able to like really kind of like figure this out and like say that the random forest is the better model here. In the case of the light GBM, so the last 3 rows, it's a bit more confusing, and the two frequency model fail here. And this is an example from a series of course, like experiment that I run, and it's a very typical thing, and that's which is why I want to kind of highlight it. That seems to happen a lot, and you can see why the light GBM one kind of fails here from the results you get from the Bayesian analysis. If you look at the orange vertical lines again, you see that close to 60% of the density is within the rope, and so just around 40% or so probability that the light GBM model is actually better. So in this case, the Bayesian model gives you some more information and like to help you like make this decision to say maybe these models are equivalent, while in the other cases you could just be either pass or fail of the hypothesis. And in this case, it just passes because the light GBM does a little smidgen better, but you don't have that context that you get from Bayesian analysis. And this is in the logistic regression case versus random forest. You can see why it's very smooth and all methods get it right, because most of the density, the probability is very much outside here, and it's easier to see that with the Bayesian analysis. I also showed the result of kind of like an upgrade update system where similar model classes applied on an update in the data set, and the same kind of like scenario from before plays out here. And these are kind of illustrative examples as well, but you can see that Bayesian test is able to kind of like source out things a little bit better and be able to say that the models are identical more or less. And then you can see again why that is the case here. The entire density is within rope, so the probability that they are equivalent is pretty much 1. And so the takeaways from this analysis is that overall, the Bayesian applications that I looked at here, I mean, both methods can work depending on the setting, but the Bayesian methods provide more information for you to make decisions, and you can, set up automatic decisions where you can say, if the probability of, model A being better is greater than 70%, or also 90% or 95% statistically, kind of like analogous to what you say, in alpha in frequentist analysis, then, model A is better, and then, you can push that down in the pipeline, and then, after further review, of course, if there's further steps down, as we have, then you can promote the model into the model that's kind of like, you serve. Or if, if probability of rope is, greater than 90%, then, you can't do that. However, it takes a bit longer to kind of train compared to the frequentist models, of course, but in our application, in my use case, this works. So just the very last slide before I conclude, to kind of like tie things back together, is that having done all this kind of validation, and in our setting, we then do a bit, consider a few more things, like, we check for bias metrics and fairness, because we want to be equitable in the access to, insurance and things like that. We have governmental kind of regulations to kind of consider as well, so we take those into consideration and look at the risk assessment, how this model, what kind of exposure it gives to, we get out of using this kind of models. So overall, that's kind of like ties up all the consideration we look at for a kind of application like this, and hopefully we have a few moments for some questions from you guys. Thank you.
Thank you. Emmanuel, Manav, any questions? Any questions?
So there are two things, right? So you can run both models in you can run the new model on a shadow mode, or you can run in a A/B fashion, or either so you say a model. So one is active, and the both models are active, but one is getting 20% of the traffic and etc. So in that sense, you have to get the errors and also have to figure out like where to stop that tracking, right? Do you have a, just want to get your thoughts on how do you track and how do you also get the errors so they are consistent, they're significantly, they're statistically significant.
That's a good point. So I think I can answer one part of your question where you're talking about different types of deployments. There's like you talked about like an A/B tested situation where you're testing two different models, right? I think we could call it a canary situation where you're directing some traffic to one model and directing some traffic to other model. Our cases kind of are somewhat complicated in the sense where we can't have two models flowing at the same time because we have to have like more regulatory control over what we're sending it. So like if like for example, two models out there, one produces one risk class for a person and another person is produce a different risk class, the other model person produces a different risk class, then that's like opens us to lots of class action losses, I guess. So there's like, so we have to be very, very restrictive in the types of models that we're pushing out. And so online testing essentially it's kind of complicated for us. What we do is we do lots of offline stuff. So evaluating metrics for, let's say, evaluating stuff that you essentially do in your experimentation. Let's say the accuracy, the predictions, all that stuff, and seeing the quality of data, repeating that in production, and then also some of the statistical tests that Michael mentioned. Make sense?
Any other questions?
Just a quick question, actually. Yeah. I just wanted to know if you were able to use the uncertainty that you get out of the Bayesian framework for any modeling decisions. Like, how can you use the uncertainty to make like the modeling decisions out of the framework?
Would you elaborate on modeling decisions?
Getting different data or changing the modeling. So are you using that uncertainty for any other modeling?
Yeah, not right now, but I can see how that can be used. You can, for example, like if you look at some of the graphs I showed, I mean, the uncertainty, if you look at the width of the distribution, kind of gives you like kind of a notion of how certain it is around certain situations. So I can see that being used, but at the moment, no.
That's a good idea.
Any other questions?
Thank you for the talk and giving an interesting framework for doing this. I have a question about deciding on how big of an effect size is meaningful. How do you go about deciding what that effect size is? And then even if you've decided an effect size, how is the Bayesian approach different from hypothesis testing, but just having your hypothesis be that the means are not equal, that they're just less than or equal to 1 or 0.1 or whatever?
Yeah. I mean, the effect size is something you decide on a case-by-case basis based on your application. In terms of, I mean, what you are trying to do, I mean, at least what I was modeling in the applications and the examples I was showing is that that the main differences is different from 0, and certainly you can say it's different from 0.1 or 0. Something like that. But then again, it's a bit more arbitrary, and because again, at the end of the day, there are two things. One, you choose a certain number and then you go with that. But at the end of the day, you still have some of the problems that we mentioned around, for example, how correlated these samples are, and that is things that are not handled. And so overall, you still have a higher value of type 1 errors that arise in this case compared to like when you use kind of like Bayesian and specify something like a rope. I mean, the good thing about the ropes in the Bayesian situation is that you can be very principled about what that rope is, and you can say, for most of our models in this model class, 1% is good, 5% is good, and that is fine. But in the other case, again, you just reject rejects a hypothesis, but it doesn't really say something about why you should accept something else as well. So I think the same kind of scenarios, the same kind of problems still arise, even if you move things a little bit differently on the frequentist test way.
Okay, thank you so much, guys. So we'll be moving on to, so let's give them a round of applause. Thank you.